All right, in this video, I wanted to go through some of the applications of linear systems from chapter 1 that we didn't get to cover at first. So our first application is just going to be about network flow. So if we have a certain number of sources, or if we have a certain number of paths along which things are traveling, so traffic or electrical circuits, we can actually balance the load on these different paths by using linear algebra, trying to solve a system of equations. And so if we have any kind of network, we have certain points called junctions or nodes, and then we have different branches that allow us to figure out where different things are going to go. So maybe this is people walking in the school and taking different paths to class, or maybe this is people driving on the road, all that good stuff. So we usually will tell you, the direction of the flow. Okay, it's implied that if you're going on a path, you can only go in one direction. Okay, and then the amount that is flowing that way. Okay, the key assumption that's going to help us balance these things in is the idea that rate out or rate in equals rate out. Rate in equals rate out. And that helps us set up equations using each of those junctions, right? So at each of the junctions, how much is this 45 is coming in, it has to be balanced in between x1, x2, and x3. Okay, so rate in 45 has to equal rate out, x1, x2, x3. So our first example will be about traffic flow. Okay, we'll just do one example of kind of each of these things. So we've got a roundabout here. And you can see that I've kind of hand illustrated this, so I apologize. And I've gone ahead and I've labeled some things. Number one, we've got our actual traffic circle in the middle, going all the way around. But number two, we have several entrances and exits. And I've labeled the flow by using an arrow to tell you which one is an entrance and which one is an exit. Okay, and each stretch of road is one of our branches, a path on which there could be cars. The numbers that are here represent the estimated number of cars that are either coming in or coming out of that branch per unit of time. We're not really worried about the per unit of time, but obviously if you were making an actual judgment, okay, maybe you wouldn't want this to be 100 cars a minute. Okay, maybe you would want this to be 100 cars every 30 minutes or something like that. But right now we're just kind of focused on how would we actually use the linear algebra to balance this. So when we say something like find the general solution of the network flow, we're asking what solution, what vector, represented by the 6 variables, x1, x2, x3, x4, x5, x6, will balance out all of this traffic flow so that, maybe not everyone ends up on x1. We can't have all of this happening at x1. That's how we get traffic jams. So how do we kind of keep everything balanced? So what we're going to do is, in order to set up a system of linear equations, we're going to look at each node, okay, as where we have that rate in, rate out. So we'll look at each, I've labeled them with letters, A, B, C, D, E, and F. We'll look at each of those and write an equation that represents that. So for example, for node A, I notice that what's coming in is x1. So wherever the cars were before, okay, if they ended up on x1, they're coming into that node A. And the rate out, 100, will be leaving. But whatever else is left will be going on the path x2. So let's just keep going around the circle. For B, I can see that x2 is what's coming in, and 50 is what's coming in. Notice the cars are entering right there where it says 50. And what's coming out is all of those cars have to go out on the path x3. For C, I've got x3 coming in, and leaving is 120 cars, and however many end up on x4. For node D, I've got x4 coming in and also 150 new cars entering, and they all have to go out on x5. For E, okay, I have X5 cars entering, but then I have 80 cars leaving, and however many else end up on X6. And finally for F, we've gone all the way around the circle. For F, I have X6 coming in, along with, 100, and all of them have to go out on X1. So this gives us a kind of series of equations to work with. What we would like to do is, unlike the application we did with chemistry, what we would like to do is we would like to isolate all of the constants on the right side. This is not going to be a homogeneous system of equations. This is going to be a heterogeneous, okay? It's going to be equal to some constants. So I'm going to rearrange each of the equations so that all the variables are on the same side. X1 minus X2 equals 100. X2 minus X3 equals negative 50. X3 minus X4 equals 120. X4 minus X5 equals negative 150. X5 minus X6 equals 80. And, oh, I forgot my 6 on that last one. X6 minus X1 equals negative 100. Okay, so we can make a matrix out of this. Each column of the matrix is going to represent one of these variables. So our matrix, okay, column 1 is going to be X1. So in the first equation, that's 1, second, 0, 0, 0, 0, negative 1. Okay, second column is X2, negative 1, 1, 0, 0, 0, 0. Okay, X3, 0, negative 1, 1, 0, 0, 0. X4, you can see how this is going. We're kind of getting some kind of like upper triangular matrix-ish. Okay, we're on X5 and X6. And then I didn't leave enough room for it, but we want the augmented part to be the constants. So 100, negative 50, 120, negative 150, 80, negative, oh no, there we go, negative 100. Okay, and then to balance this, you would row reduce. Okay, so row reduced echelon form, and for the sake of time, let me just go ahead and tell you what we end up getting. Okay, we do get some free variables. Notice that there are more columns than there are rows, so we will have free variables. And that free variable ends up being X6 in this case. And our equations, if I solve for each variable in which there is a pivot, I get X1 equals X6 plus 100, X2 equals X6, X3 equals 50 plus X6, X4 equals negative 70 plus X6. Maybe I should have kept them in the same order. X5. Let me actually rewrite that. That's going to annoy me. So X3 was X6 plus 50. X4 was X6 minus 70. X5 is X6 plus 80. And then X6 is free. So if we were to write the general solution for that balances this traffic circle, I've got, oops, give myself some space here. I've got all the coefficients of X6, so 1, 1, 1, 1, 2, 3, 4, 5, 6, okay, plus the vector full of constants. So 100, 0, 50, negative 70, 80, and then remember, I don't want the free variable to be dependent upon any other constant, so I'm going to put 0. And so that's how you would describe it. If you think about finding the smallest possible value for X6, so what is the least number of cars we can have here? Okay, maybe we need to like close the road and do some kind of maintenance. Okay, well, how much can we close the road? the smallest possible value for x6, you want to look at your equations and you want to say to yourself, well, I certainly do not want x4 to end up being negative, right? Because if x4 is negative, we end up getting cars going in the wrong direction. That's when we end up getting that backup that we do not want. So to keep traffic flowing, we want x4 to be greater than or equal to 0. I guess there could be no cars on x4. That's fine. Okay, so that means we would want x6 to be greater than or equal to 70. So x6 is really important here, depending on our unit of time. If this is over 2 hours, maybe that's not so bad. But if it's in the next 30 minutes, we definitely need to keep 70 cars going on x6. Then maybe we need to think about our methods of rerouting traffic. Okay, so that's how to find a general solution when we're talking about network flow and applying it to kind of like traffic circles or walking patterns, that kind of thing. A little bit of civil engineering here. So our next application is going to be similar in that we are mapping kind of the travel patterns of something around a loop. Okay, we're going to talk about current flow, and we're going to also describe each flow kind of as a linear equation. So there are two really important ideas that we need to have in the back of our mind as we are figuring this out. Okay, so a little bit, I'm not going to get too complicated here, but a little bit of physics. And it's this idea that the voltage equals the resistance times the flow. Okay, so we've got our voltage in volts coming from that source, kind of a battery or something like that. The resistors might be different, like light bulbs, objects, anything that they have to kind of push that through. And the current flow is in amps. What helps us actually set up the equation, okay, is that the algebraic sum of the voltage drops in one direction around a loop equals the algebraic sum of the voltage sources around the loop. So it's kind of another rate in, rate out problem, but this time it's like drops have to equal sources. Now this might, if you're not in physics, this might have a couple of symbols here described in this image that are a little bit unfamiliar. So our little variables that are in the middle, I1, I2, I3, and I4, all of those are going to represent that current flow. And they're all right now drawn in the diagram as kind of going counterclockwise. That might not necessarily be true. Okay, these are obviously interacting with each other because there are some resistors that are shared. But instead of looking at the entire current flow around all the outside, we can break it down and look at little individual pieces. And so whenever you see the squiggly line, like you do here, okay, that is a resistor. Okay, I'm resisting with a force of kind of 1 ohm there. And the little double lines that you see here at the top, that is our source. Okay, and generally, okay, when we're actually going to add in some arrows ourselves, our flow, we flow from positive to negative. And what that looks like in terms of the source is that here is the positive end, a little bit longer, the negative end, a little bit shorter. Okay, so we would flow from the positive around to the negative. Okay. And what we're going to do is, just like we wrote an equation for each of the kind of nodes here, in this example, we're going to write an equation for each of the loops. So we're going to have 4 equations, loop 1, loop 2, loop 3, loop 4. Okay, so again, the sum of the voltage drops in one direction has to equal the sum of the voltage sources in the same direction. So for the first loop, I'll highlight that in pink here. Okay, our voltage source is 40. So let me say loop 1, the voltage source is 40. That's this kind of battery here. There are no other, I'm calling it a battery, but whatever it is, there's no other sources on this one loop. This has to be equal to our current times the resistor. Okay, those will be our voltage drops. Okay, and that's where we get this V equals RI. Okay, resistance times current. Okay, or that kind of flow. So, and we're gonna have to be careful because we are, again, flowing from positive to negative. So that means, in this case, flowing this way. Okay, but as we look at the next example, this loop is also being interacted with the second loop. And the second loop is flowing this way, in the opposite direction. So that's going to interact with what we write down for loop 1. And similarly, loop 4 is also interacting with loop 1. In this case, if I'm going from positive to negative, I'm actually drawing the arrows in the opposite direction of what was given in the diagram. Okay, but I always like to do it from positive to negative. So if we take a look at loop 1, we're going to have to interact with not only I1, okay, that current in the top left, but also I2, current in the bottom left, and I4, current in the top right. So this 40, okay, is going to be equal to, let's take care of all the I1s first. Okay, 1I1 for that first resistor here. Okay, plus 7I1 for the second resistor, plus 4I1 for the last one. But it's also interacting along the middle lines, those kind of border lines, with I2 and I4. Notice that I2 is going in the opposite direction. So we have negative 7 I2. And then for the blue one, okay, so for I4, it's going in the same direction, so we'll do plus 4 I4. Okay, so we have to think about the direction of the current flow when we are kind of adding up all those resistors. So that's loop 1. Let me combine everything a little bit just so it looks prettier. So 40 equals how many I1s? 12 in general, 12 I1 minus 7 I2 plus 4 I4. And so we're going to repeat this process for all the loops. So I'll go to loop 2. Okay, so my source in loop 2, it kind of got cut off here, but it's supposed to be 30. Okay, so I've got 30 as my source. Okay, and that's going to be equal to, let's go ahead and go all the way around to I2. 2I2 plus 6I2 plus 7I2. Okay, and then let's worry about the other ones. It's interacting with I1 in the opposite direction, minus 7I1. Okay, and then I need to pick another color here. Okay, for our last loop, I3 flowing from positive to negative. Okay, so it's flowing in the opposite direction of I2 on that border. So I have minus 6 I3. Okay, combining those things, I have 30 equals 15 I2 minus 7 I1 minus 6 I3. Okay, keep going. I'll go back to using red. Okay, loop 3. Okay, my source is 20 in this case. I've got 3 I3 plus 5 I3 plus 6 I3. And then it interacts with I4 and I2. So we're going the opposite direction of I2, minus 6 I2, in the same direction as I4, plus 5 I4. Combining everything together, I get 20 equals 14 I3 minus 6 I2 plus 5 I4. And last but not least, woo, loop 4, source is 10. That will be equal to 5 I4 plus 4 I4 plus 4 I4. Obviously, you don't have to write out all this work when you're doing it, but it helps me kind of keep everything organized, make sure I've got the right number of resistors. Okay, same direction as I1, so plus 4 I1, and also same direction as I3. So plus 5I3. Cleaning that up, I get 10 equals 13I4 plus 4I1 plus 5I3. And now, okay, I am trying to balance that current flow. Okay, balance that out. And I've got a system of equations going on. Now, again, just like in our last example, I don't have a homogeneous system. I have a bunch of constants, the 40, 30, 20, 10. So this is going to have to be an augmented matrix. Each column is going to represent the coefficients of I1, I2, I3, and I4. So my matrix looks like 12, -7, 0, 4, -7, 15, -6, 0, 0, -6, 14, 5, 4, 0, 5, 13. Those are my coefficients. My augmented part is 40, 30, 20, 10. Okay. Once I have row reduced, okay, obviously in my calculator, again, notice I'm getting more columns than rows, therefore I'm going to get a free variable. Okay, actually, no, I'm not. I'm sorry. I'm not going to get a free variable. Okay, hopefully, I mean, I could, okay, but I made that mistake because I was looking at the entire matrix and not just looking at the coefficient part. Okay, the coefficient matrix is a square, so that doesn't mean anything. It could be a free variable, it could not be a free variable. But in this case, when I row reduce this, I actually got a pivot in every column, so no free variables, and I got some decimals. Okay, and that's okay in this case. I got that I1 was 11.434. Got that I2 equals 10.550. I3 was 8.036. And I4, which actually ended up being a negative number, -5.840. But that indicates that this I4 is flowing in the opposite direction of what we illustrated. Okay. So if you get a negative number, that's just what that means. All right, there's a nice little way to organize it. We could have done this a little bit faster if I had kind of combined some of the things originally, but I wanted to make sure that I was illustrating that, again, each equation is really following this equation here. Our voltage, or our source for each loop, is equal to the resistance, okay, the resistors, times that kind of flow in amps. Okay, and we add up all the resistors, including if it interacts with other things. This is kind of a concept we encountered in multivariable calculus when we were trying to find surface area. And instead of finding the whole surface area, we broke it down into teeny tiny pieces. Same thing you can do here. If you're trying to look at the entire circuit, you can break it down into smaller chunks. Our last example that we're going to do is called a difference equation. And what we are trying to do here is model some kind of system changing over time. And we might have encountered this in BC calculus because we've also talked about differential equations. Do things reach equilibrium maybe? Okay, so that's what we're gonna try to model using a matrix, because maybe there are many different changes that affect what we're looking at, population. Okay, the one thing is we always wanna make sure that we fix one particular time as the initial year, because we are going to use a matrix to describe the changes that happen every single year. And so in order to know where our population ends up, we need to have a starting point. That will give us how many times we need to apply this matrix of changes. Okay. All right. So for our example here, we've got some made up city. Okay. In a certain region, 7% of a city's population moves to the suburbs. You know what? Let's just call this DC. Because that's where we are. Okay, so in DC, let's talk about that. So for DC, okay, every year you could multiply the population by 0.07, and that would give you how many people would move out. And that means if you multiplied the population by 0.93, you would get how many people stay in DC. But some people want to live in DC. Not everyone's trying to leave DC. 3% of the suburb population moves into the city every single year. So on the opposite side, you could have, let's just call it Fairfax. Okay, Fairfax, each year you could multiply Fairfax population by 0.03, and you would get how many move out to the city, specifically to the city. And you could multiply the population by 0.97, and you could see how many people are staying. Now, obviously, we're very much simplifying the system. Not everyone is exclusively moving to the city or to Fairfax. But we're trying to keep it simple. Obviously, you could expand the matrix to include more changes or more locations that people are going to. So we're actually going to set up a vector, okay, that's going to include our initial populations. So let's say in 2000, there were 800,000 residents in DC and 500,000 in the suburbs. Okay, I actually have not looked at the population, so I don't know if that's realistic or not. A fun fact for you to pause and look up here. Okay, we are going to make a vector x naught the initial population. So the initial population, okay, we're going to call it the vector r naught and then s naught. Okay. This is going to be the city population, and this one is going to be the suburb population. Why did I use R? I don't know. We use C for a lot of other things, so just decided R. And R and S are close together. Okay. Initial. All right, so before we just jump straight to the matrix, let's actually try to figure out what would happen 1 year later. How would we figure that out? Okay, so using vectors, okay, 1 year later, okay, that would be like R1, S1, okay? I would want to multiply the city's population, the initial city's population, by, I got this backwards. Because I want each row to read correctly. So the new city population will be equal to the old city population multiplied by how many stay, plus the suburb population multiplied by how many people leave the suburbs. Okay, so that's the top row. Let me highlight that across. Okay, in the second row, if I wanted to find the new suburb population, I multiply the city population by how many left and add that to the suburb population multiplied by what percent stayed. Okay, so that's our second equation. But we can continue doing this, okay, if we can actually change this into a matrix by using our population vector and our column vectors here as the matrix columns. So I would get that the new population 1 year later is equal to this matrix multiplied by the initial population of each suburb and city in a vector. And then you could repeat that. It's kind of like a recursive function. What we're going to end up getting to later, okay, later is how could I continue to multiply by a matrix and reach some kind of equilibrium? Does an equilibrium exist? Is there some kind of resting population that's just going to eventually come to be? And we'll get to that later this year. But let's just focus on, again, solving our initial problem here. Okay, so what we could do, if we want to find, I think this problem asked us for estimate the population in the city and the suburbs 2 years later, in 2002. So they told us that in 2000, population was 800,000 in the city and 500,000 in the suburbs. 800,000 in the city, 500,000 in the suburbs. So that's the initial population. That's not. Okay, so that means 1 year later, in 2001, the new city population, the new suburb population will be this matrix we created, this kind of change matrix, which feels redundant because matrices are inherently transformations. So when I say change matrix, it's like, yeah, transformation. Okay, multiplied by 800,000, 500,000. And I went ahead and did the multiplication for you. You can check my work if you would like. But it should be 759,000 is the new city population, and 541,000 in the suburbs. And that makes sense because if we just look at the numbers, intuitively, it kind of looks like, oh, less people are staying in the city, more people are moving from the city to the suburbs than there are from the suburbs to the city. So we should be adding more people to the suburbs. So we have to do that again for 2002, okay? So we want 2 years later. So, I keep writing another R. Our next population, 2002, will be, again, the same matrix because the same changes happen every year, multiplied by our 2001 population. Now, if you are feeling savvy, and I think maybe some of you are, I think you could think of a way that we could have done this in one step, kind of in our calculator, using maybe some matrix association properties. Okay. But think about it. If it doesn't come to you, we will definitely cover it in this class. Okay, but that's our population. So our city population in 2002 is 722,100 people. And our suburb population in 2002 will be 577,900. This is some, if you don't mind me saying, this is some explosive population growth in the suburbs. That's a lot. As a teacher, that's a lot of new families and people and parents to handle in the suburbs. So maybe we should look at building some more schools if this is the way the population is going. Anyway, okay, those are our applications from chapter 1 that I found particularly interesting. Again, using either matrix multiplication or creating and solving linear systems to be able to balance out real life scenarios.